Hey folks, today we're going to look at tests that you'll do using statistics. One of them is chi-square test, when you're comparing nominally scaled variables, or might be demographic variables, uh, gender, male, female, two categories, and comparing to usage for a brand, low usage, high usage. So all your responses go into different cells in a 2x2 matrix, and then you look and see for departures on what you would expect in those different cells. And there's a statistical test for that called chi-square. We'll also look at t-tests, where you have two groups, and a dependent variable might be satisfaction for a brand. And the two groups, again, might be low usage, high usage. You're trying to compare satisfaction levels across those two groups and see if there's a statistical difference for any difference that you see there. Okay, refreshing our memories here, standard deviation. This is the spread in the data. You have a distribution. So the range of values for your variable might be 1 through 7 on a Likert scale. And so then you would drop the different individual respondents into counts for each of those categories 1 through 7. And then you compute a mean value, that would be X bar. And then for each respondent, you'd find out the deviation from that respondent from the average value. You'd square it, you'd sum all those up, then divide by the sample size minus 1, and then to put that back into the original units of the scale that you used in your measurement. Originally, you take the square root of that. And so that renders the variance to become the standard deviation. In printouts for software programs like SPSS or even Excel here, you can look at this satisfaction variable, Jose Southwestern Cafe versus Santa Fe Grill. And here you have the N is the sample size. So there's 152 respondents in the Jose's group. And then the Santa Fe group, you have 253 here in the bottom. Look at the mean. For Santa Fe, it's 4.54. For Jose's, it's 5.31. Given the spread in both of those distributions in the group for Jose's and Santa Fe, is there a statistical difference in that? And that's what you're trying to get to here in your measurements. So we have a frequency distribution here, frequency of eating at whatever restaurant it is, Santa Fe Grill. Very infrequently is the first category. The second, somewhat infrequently, occasionally, somewhat frequently, and very infrequently. So we have a 5-category or 5-point scale variable used there. And we see the different percents here. It looks like the modal value here is somewhat infrequently. And when we look at how this looks, it is the modal value, but there's somewhat frequently is just behind that. So it almost looks like a bimodal distribution. We have 2 humps in your data set here, but the bar charts depict that for us. So when we develop hypotheses, you do this before you actually would make your statistical test. You have a null hypothesis, and that represents the status quo, or the way things are understood to be now. And then your statistical test that you'll compute using statistics will evaluate that null hypothesis. So your alternative hypothesis is not the null hypothesis or whatever you're proposing in the null hypothesis. And so this is part of science. And so this is the way we use evidence and test it and statistically understand whether we have differences that matter or whether things really are the same. So here's an example. Miami, Florida is the average monthly electric bill more than $250 a month. So translate this into a null hypothesis and test it. So I think you can see that this exceeds $250. your hunch, but it probably is that the commonly understood perspective on an average monthly electrical bill is that it is equal to or less than $250 per month. So that would be the null hypothesis. So your null hypothesis X sub zero, the average monthly bill X bar is less than or equal to $250. And the alternative hypothesis, you could state it as not H sub zero, or you could spell it out H sub one, the X bar is greater than $250. All right, so we can also do tests against a standard. And so here in the example in our textbook, the owners of Santa Fe Grill want to understand whether their prices are perceived to be reasonable or not. So on a 7-point scale, 4 would be the midpoint. And so they're trying to see if their the perspectives or the responses about reasonable prices are different than the midpoint value or even less than that. And so here, the results suggest that there's a t-value of 5.40, and the significance of that is very strong. So it's way out in the tail of the distribution. And so that is, we could say there is an expectation that prices are reasonable, okay? But I think there's improvements that can be made there. All right, so in other tests that can be done, there's chi-square test using nominal data. This is done frequently in marketing research because you have demographic variables and you're trying to understand your segments, and many times those are defined by demographic variables: age, income, education, region of the country or zip code, usage level, those kind of demographic variables. A lot of those variables come up at the end of surveys. So marketers use those to better understand, I guess, the profile of their customers and their segments these customers might be in. And then they buy media according to what fits those different profiles. There's the t-test where you have a dependent variable. It might be this satisfaction variable, but you look at two groups, and it might be those that live in cities, those that live in rural areas, and you'd see if there's a difference in satisfaction for your brand across those two groups of customers. Bill Neal, Lifetime Achievement Award winner from the American Marketing Association and founder of SDR Incorporated in Atlanta, he says cross-tabulation still remains the most frequently used data analysis technique for marketers. There's more to use than crosstabs, though, and then Bill spells that out. This is the algorithm for computing a chi-square value, and it's not rocket science. I mean, there is, some Greek letters here, but you just, in your matrix for, you look at your observed value for each cell, and you subtract the expected value for that cell. You'd square it, and then you'd go across all of your cells in your matrix doing that, and you'd sum all those. And then you divide that by the expected value for those cells. So here you see the depiction of this down below. Could be that there was 188 in a cell and expected to have 176. You'd square that difference, divide by what was expected, 176. You do that for the next cell, you do that for the next cell, you do that for the next cell. So this is a 2x2 matrix, and that computes to a chi-square value of 7.05. And with the 1 degree freedom chi-square test, the critical value for the 0.05 level at 95% confidence is 3.84. So 7.05 is beyond that. So you're out in the tail. And so you would reject the null hypothesis that there's no relationship between these variables. And you would say there is a relationship. We'll see this depicted graphically here in just a minute. Okay. This example from the book here has to do with distance-driven variable X sub 30. And here we see that there's the distance driven to the restaurant. One group, less than 1 mile, 1 to 5 miles, more than 5 miles. And then you can see here in this, the expected count for each of these. This is the count actually for these cells. So this column is the male coded. This is the female. So the columns represent gender, and the rows represent the distance driven to the restaurant. So here's the count, 74 and 12. It's at the top of each of these cells, 45 and 31, 57 and 34. And then you have the totals down here, 176 males, 77 females. And then you're going to make these comparisons between what's expected and what you have there. So you'd be subtracting the expected from the observe, and you'd square that. We can see here that with regards to the less than 1 mile, 86% of those that are driving less than 1 mile to the restaurant are males, 14% female. That gives 100%. When we drop down here to the 1 to 5 miles, 59.2% are males, 40.8% are females, and then 62.6% are males, 37.4% are females. So what we would expect if things were evenly spread across these cells, you'd have 30.4% in these cells. But here it looks like a departure from that. 14% is low, 40 is high, 37% is high. So we go to our chi-square test, and the chi-square value is 16.945, and that has a p-value of 0.00, so far out in the tail of the distribution. So we would reject the null hypothesis that the status quo is that there's no relationship between gender and miles driven to the restaurant. So it appears that for some reason, women are more likely to get in their cars and drive far to the restaurant as opposed to men, who apparently might walk there. So if we knew the geography of the restaurant, we might realize that maybe there's a military academy nearby the restaurant, and it's mostly men, and so they're walking there and getting some food there after hours and on the weekends. All right, so kind of the decision rule for if you have a 2-value variable and you're cross-tabbing that by another 2-value variable, you'd have 1 degree of freedom there. So to determine the numbers of degrees of freedom, you'd have the rows minus 1 times the columns minus 1. So here we have 2 rows and 2 columns, each subtracted by 1. You multiply 1 by 1, that's 1. So that's a 1 degree of freedom, and that comes up as 3.84. So when we go to the chi-square table, we can see that this is the column for making that test using 0.05% as our level of significance. And so it corresponds to marking off this part of the distribution just to the right of that chi-square value. So depending on how many rows and columns you have in your matrix will determine what row you go to here to compute your critical value for this point in the on the baseline for your distribution. So here, a 1 degree of freedom chi-square test, the 0.05 level here puts it at 3.84. So if you have a value be greater, chi-square statistic greater than 3.84, you're going to be out here in the reject region of the distribution. You reject the null hypothesis that there's no relationship between the 2 variables, and you would say there is a relationship between those 2 variables. And if you had a more complex matrix, you'd come up with these computations for the degrees of freedom, and then you'd compute this critical value here that is the threshold. To the right of that, your chi-square statistics indicate that you should reject the null hypothesis. And if you're over here on the left side, you do not reject the null hypothesis. Okay, there are some cautions with chi-square tests. You have to have more than 5 counts per cell. So sometimes if you have 4 to 5 columns or 4 to 5 rows, your data set is not large enough and you start getting spread or your cell count in these cells, it drops below 5. When that happens, you can't use the chi-square test. The action there is to actually recode your columns or your rows into fewer columns and rows, and then you do the test with those fewer columns and rows. And also, these tables don't show conclusively causality, but just that there's a relationship often points to insights that are important for managers that these two variables are related. Okay, moving on here. When we look at t-test, we're making comparisons and we're going across two groups and we're trying to see what's different there in a dependent variable. So there's different tests of differences. You can have a one sample t-test where you're comparing against a standard. We saw that previously when Santa Fe Grill was trying to understand if their price reasonableness was different than the value of 4. Okay, then we have two independent samples t-tests. So we have two groups, two subgroups in your data. It might be males and females. You're comparing them on a dependent variable. It might be likelihood to purchase. Paired samples, here you have the same individuals in both of your comparison groups. So it's identical respondents in one group, identical respondents in the next group. When you do that, your precision level goes up quite a bit. So it's very attractive to do that. Sometimes in marketing, or there might be longitudinal studies. You'll test people in the spring, and then you'll test people later in the fall to see if there's any change in attitude. And you're doing it with the same people, and so that's a paired samples. And then you have more than 2 samples. That's an analysis of variance, so that's multiple groups, more than 2 groups for that. Okay, related samples, we just talked about that. You got to have the same respondents in both groups, and when you do that, that's good science. You're moving up there in your accuracy and precision. Okay, so the t-test here is you're comparing the subgroup means from each other, and then you're taking a standard error of the differences between these means. So everybody, all your respondents have, or your respondents across your two groups have differences. And so that computes your Z statistic. And so here we have an independent samples t-test. Looks like the comparison groups here are male and female, and 176 males, 77 female. We're looking at the satisfaction with Santa Fe Grill. We see that the mean value, the guys are higher here than the women, but is that a statistically significant difference at the 0.05 level? In other words, it's a difference that 5% of the time will accept an error. So 1 out of 20 times making this test, it might be misleading, but we'll accept that rate of error as we go and make our tests here. So when we drop down here, let's say that the equal variances are not assumed. So the t-value here is 4.21, and our degrees of freedom are quite high. Significance level is 0.0. And so here that difference of 5.17 is statistically significant at the 0.05 level. Guys are definitely more satisfied than women, which should lead managers to either understand what is it on the menu or in the service that makes the guys prefer this than the women. And then they can troubleshoot and come up with new options for ladies, for example. Okay, so this paired samples t-test, you would use the same respondents that would be in your first group you're comparing and the second group that you're comparing. All right, so here we have the same respondents, and so here we're comparing 2 means with the paired samples t-test. So we know that the respondents are the same, and here trying to compare food taste rating with food temperature rating. And so what we get here is that there is a, when we get the t-test here is 8.42 for this difference. We see the difference here is 3.95 with the standard deviation of 0.747, and that leads us to this significance value of 0.000. So there is a difference. So the taste is better than the temperature. Again, you can work with the service staff. Perhaps the dishes are remaining up on the pickup line too long, so they get cold, and so maybe you need to have more wait staff hired to solve that problem. Okay, so analysis of variance. This is when we go to compare multiple groups. We'll look more about analysis of variance when we go to the second part of our chapter 11. Okay, type 1 and type 2 errors. Type 1 error occurs if the null hypothesis is rejected when it's true. So in other words, you see false positives, so that you should make a change. So there's indications that you should make a change when actually you shouldn't. Okay, and that's a type 1 error. Type 2 error occurs if the null hypothesis is not rejected when it is false. So in other words, you stay put when you should have changed. Okay, that's a type 2 error. Okay, so we get alpha is associated with type 1 error and 1 minus alpha over here with type 2. We get this matrix here of the null hypothesis being true, but yet you choose to reject the null hypothesis. This is type 1 error. And then we go over here, type 2 error, where the null hypothesis is false, but you chose to stay with the status quo. So probably in management, this one is more given attention by managers, but actually the consequences are different. This is an opportunity cost, an opportunity lost. So you should have developed a new brand extension and you didn't. And so your market share shrank, and now you can't respond effectively in the marketplace. So you really need to be focused on developing your brand, and do keep in mind that trying changes is part of developing your brand, and not every one of them is going to work out, but probably the real killer is if you do nothing, you sit on your hands, and over time, the market passes you by, and somebody taps you on your shoulder and says, your time here as brand manager is up, and somebody else is going to lead the effort now because you were too timid. Okay, so here's an example. A sample of bookstores. The average weekly sales for the unsigned book is $29,000. The average weekly sales for the autographed book is $30,000. So it looks like there's a difference, but is there? All right, let's go to our setup here. So here we have the mu, which is the population parameter, which here's the population mean, is proposed to be less than or equal to $29,000. So that's the kind of common wisdom, or the way things are understood right now, the status quo. The alternative hypothesis, the population mean, is greater than $29,000 if you put a autograph on that book. So there you would compute a critical value, that threshold for where you're going to make a decision in your T distribution. So here it's 1.645. It's a one-tailed test, and at the 0.05 level, actually all of your one-tailed tests will have this value of 1.65. And so here you make your test statistic. It's actually 29.65 or $29,658. And you make your computation here for your Z value corresponding to 30,000, which is 2.5. And then we go to our T distribution here. This is the population mean value of $29,000. We transform that to a Z value of 0. And then we see here that the critical value here is $29,658, which corresponds to the z-value of 1.645. And so if we did have $30,000 as our measured value for the average income for autograph book sales, we would see that was the be out here to the right side of our reject region. And so we would reject the null hypothesis that the autograph sales are the same or less than the population mean value of 29,000. And we would say, yeah, there is a difference, and autograph those books and get them out there. You're going to make more money when you do that. Okay, now let's take a look at two-tailed hypothesis test. So in the two-tailed hypothesis test, you are looking at, it could be either way, on the left or the right of that mean value for your population. So here it is, men's income and then women's income is 2. So if you subtracted the women from the men, you'd have the 0 value here. And now you're trying to see if there's a difference between the men and the women. And it could be higher, it could be lower. So if the women's value is higher, it's going to be over here on the negative side. And that's going to be a z-value of minus 2.29. Your critical value here, by going to the tables, is minus 1.96. And if the women's is less than the men, so when you subtract U2 from U1 or mu2 from U1, then you're going to have a value that's out here in the reject region. So it's a two-tailed test. It's not as strong of hypothesis as the one-tailed test where you're saying it's definitely going to be on one side of the mean. Here it could be either way, less or more. But you do have these critical values here, 1.96 and minus 1.96. These values stay the same. So that's the z-value for making a decision using the 0.05 level. So you've got 2.5% of your distribution out in the left tail and 2.5% out here in the right. And so that always comes up. So these are a way to simplify your understanding of statistics. The 1.96 value plus or minus is always there for a two-tailed test. The 1.645, either minus or positive, is always there for a one-tailed test. That concludes our focus here today on chi-square and t-test. Join us next for our focus on analysis of variance.